Welcome to Green Giants, Titans of Renewable Energy, a podcast where insights and innovation meet. Every episode, we dive into conversations with industry leaders, experts, and change makers, bringing you the stories and ideas in the renewable energy sector that shape our world. And now, let's jump into today's episode with your host, Wes Ashworth. Welcome back to Green Giants, Titans of Renewable Energy. Today's conversation is about a hidden bottleneck in the energy transition: materials. We talk constantly about renewable power, EVs, AI data centers, and grid expansion. But all of that depends on copper, steel, aluminum, and other physical materials that may not scale fast enough or perform well enough for the future we're trying to build. My guest today is Bryan Hassin, co-founder and CEO of DexMat, the company behind Galborn, an advanced carbon material designed to be lightweight, strong, flexible, conductive, durable, and scalable. Bryan also co-founded Third Derivative, one of the largest climate tech innovation ecosystems, and he has spent his career building companies at the edge of climate, energy, and deep tech. This episode asks a big question: what if the energy transition cannot happen without a materials transition? With that, Bryan, welcome to the show.
Thanks. I'm really excited to be here.
I'm super excited to have you, super fascinated with this topic and to get into it. But as always, we'll kind of start a little bit with your story. So your story is unusually full circle. Your path runs through Rice University, Rick Smalley's influence, software entrepreneurship, climate tech ecosystem building, and now the challenge of scaling a breakthrough material from science into industry. And, most people don't build their career around a single lecture. You did. And so what did Rick Smalley say at Rice that just changed the trajectory of your life?
Yeah, it was really cool. I had grown up kind of in and around literal moonshots. My mom was a curator at the Smithsonian National Air and Space Museum. So I always had in my mind from an early age that, we should be shooting for the moon. I didn't really want to be an astronaut. I'm kind of afraid of heights. That seemed risky, but I always had in the back of my head, I'm going to find my moonshot. I played football at Rice University where every game was a moonshot. We were always going to count it out, but we found ways to win. And then, actually, I had already graduated. I'd come back as a young alum. I was already an exited founder, actually, at this point. I'd sold my first company. And I had the privilege of attending this lecture by Rick Smalley called Be a Scientist, Save the World. And so he's one of Rice's Nobel laureates. He could kind of do whatever he wanted at this point, but he became very passionate late in his career about the energy challenge. And his argument was that if you took the top 10 challenges facing humanity over the next century, so energy, yes, but also hunger, water, social equity, etc., if you could solve energy, you could kind of get the solutions to the other challenges for free. And that was like a profoundly epiphanal moment for me. I knew I wanted to keep entrepreneuring, but now I had kind of a why. I had a reason to entrepreneur, which was pretty exciting. And it kind of helped me redirect my entrepreneurial efforts to explicitly focus on energy, climate, and kind of leaving the world better than we found it.
Yeah, I love that. It's extremely powerful. And I love that it just shows how one idea, heard at the right moment, can just shape decades of work and kind of send you in that direction. So again, great. Love that story a whole lot. And so as we talked about, you've built software companies, climate ecosystems, and now a materials moonshot. What did you finally see that made you say, I have to work on this problem myself?
Yeah, so my career began in software. Right? I studied computer science and electrical engineering as an undergrad. And so even once I had kind of had this epiphanal moment and decided, hey, I want to make the world of energy and climate a lot better, it really started with software startups because that's what I knew. Eventually, it became pretty obvious that it was going to take more than software to build a sustainable, prosperous, equitable future. And so I kind of pushed into deeper and harder tech. And again, I felt like I was kind of fulfilling this Rick Smalley admonition to be a scientist, save the world. When it turned out that hard tech was hard, I built Third Derivative, which is really meant to kind of help all of the hard tech and deep tech entrepreneurs out there working in climate kind of work better, faster, stronger, et cetera. And I'm really proud of the work that we did at Third Derivative. Still going, getting better every day. But at this point, we've mobilized more than $4 billion into more than 300 deep tech ventures for climate. In order to do that, we looked at thousands of ventures, thousands of technologies, and a few things became really clear kind of all at the same time. One is that metals are some of the biggest greenhouse gas contributors to climate change, full stop. And we have a number of ways to kind of work around the fringes of metals, but we don't really have a credible way to decarbonize them whole cloth at significant scale. 2 of the thousands of climate tech ventures we saw, almost 100% of them relied on rapidly scaling use of conductive materials. Yet forecasts for the production of materials like copper, which predominant conductive materials, were like declining, not increasing exponentially. And so it was clear that conductive materials become the bottleneck for most climate technologies, from electrification, EVs, renewable energy, et cetera. And then three, again, of the thousands of climate tech ventures that we were looking at, very few of them were pursuing transformational approaches to metals, conductive materials. So it was a huge gap in deal flow. And of course, to an entrepreneur, a gap looks like an opportunity. And so it was very clear that that's, as someone trying to optimize his life around, or certainly his career around impact and climate, like there was no place where I could have more impact than in materials.
I love that so much. And I always love the serial entrepreneurs, just seeing that, you see that bottleneck and immediately your mind goes to opportunity and like, how could I solve this problem? And I think that perspective really matters. What you saw through third derivative, just you were seeing patterns across an entire ecosystem, not just inside one startup, and exactly why this conversation is so important. Sometimes those biggest constraints are really hiding in plain sight. So the energy transition is usually framed around generation, storage, transmission, permitting, and capital, which we talk about a lot. But I know you're pushing us to add another layer, which is the physical materials that make every one of those things possible. So you have a line that stops people. There is no energy transition without a materials transition. Tell us a bit more about that. Why is that true?
Yeah, I guess I would suggest that I'm not trying to add a layer. I'm trying to recognize that the layer is there. So energy and materials are inexorably tied together. Like it takes tremendous amounts of energy to produce materials. It takes tremendous amounts of materials to produce energy. We can't change one without being constrained by the other. And so as a few specific examples, and these are ones that, again, this is part of my own learning journey when I was running third derivative. So fossil energy requires about 1 ton of copper per megawatt of generation. Renewable energy requires more, kind of 2 to 12 tons, depending on the flavor, per megawatt. So if we wanted to convert the entire coal generation in the world to renewables, which I would love to do, and it would require 20 million tons of copper. Now, we only produce 20 million tons of copper a year, and spoiler alert, it's already spoken for. We don't have a bunch of surplus capacity lying around. And again, it's actually getting harder, not easier to produce copper. So, okay, that's a challenge. We can't just wave a magic wand and assume that tomorrow everything will be renewable. Similarly, if we want to go the other direction, let's talk about decarbonizing some of our materials. We want to decarbonize steel by using combinations of green hydrogen and electric arc furnaces, really cool technologies. Electric arc furnaces use a lot of copper. There's another 1 million tons of copper if we want to decarbonize the global steel industry. But the massive energy need required to energize that process with green hydrogen require another 20 million tons of copper. So here, put it all together, we've already got 40 million tons of copper that we don't have no way to get out. So we're kind of stuck in this Gordian knot of energy constrained by materials, materials constrained by energy. And the only way to cut that Gordian knot is to remove the constraints with new materials.
It's such a clear way to frame it. And copper can sound boring until it becomes the very thing slowing down the future. And so those numbers you just rattle off there, you see the need crystal clear and why this needs to happen and why it's a serious constraint. So everyone, is obviously talking about AI's electricity demand, is another piece of this. What is the part of the AI build out almost nobody is talking about? And maybe you started to hint on it there, but anything else to add?
Yeah. So when it comes to AI, everyone's focused on energy and speed to energy, and rightfully so. And again, I repeat myself that we can't talk about energy without talking about materials. So in the US alone, we're trying to build 150 gigawatts of new data center capacity by 2030. Not by 2050, but by 2030. So unless things radically change about the way we make data centers, that's going to require 4 to 5 million tons of new copper. And again, we just don't have it. And that's just for data centers. That doesn't include the copper for the power generation or the transmission and distribution outside of it. So everyone's talking about the energy. Even if we had all of the energy that we needed, we run headlong into this other wall. And so we've got to be talking about it. Otherwise, we're going to be really surprised and really disappointed.
Absolutely. It's the hidden layer people miss. The digital economy and AI talking about all this stuff still depends on very real materials, very real constraints. You've said this as well, too, but I want to just, if there's anything else to add. So just for anybody that's thinking, why can't we just mine more copper, recycle more metal, and make existing materials cleaner? Like, what else is there to add with that? Like, where does this logic break down?
And first of all, we should do all those things for sure. And I humbly submit that it won't get us there. So Bob Friedland, who's forgotten more about mining than I'll learn in my lifetime, made headlines earlier this year when he pointed out that we'll need to mine as much copper over the next 18 years as we've mined in the last 10,000 years. And that's just to keep up with kind of 3% GDP growth. That doesn't include exponential growth of renewables, electrification, data centers, et cetera. So, okay, no problem. We need to find more copper. We're humans, we're explorers, we're good at finding stuff. Oh, wait, in the last 35 years, only 5% of new copper discoveries have been discovered in the last decade. So it's actually, we're finding less and less new copper. It's becoming harder for us to find new copper. No problem. We're enterprising, efficient engineers. We'll just mine our existing mines harder. Wait, copper ore grades are on the rapid decline. They're down about 90 since 1990. So it now takes 500 tons of rocks just to produce 1 ton of copper. And by the way, and this should not be controversial, climate change is happening. 10% of copper mines are already impacted by climate events, ironically, both by droughts and also by floods. And that's expected to rise to over 70% just over the coming decades. So mining what we already have is getting harder and harder. So no, we cannot mine our way out of the conductivity crisis. There are some really great technologies out there, some of which I've invested in, that improve mining productivity with microbes, reduce the environmental costs of mining, increase recyclability, scrap, et cetera. We should all do those things, but all they can do is kind of bend the curve. They can't get us out of the inevitable supply-demand imbalance of today's conductive materials that's coming, again, not in decades, in years.
Yeah, just thinking about those figures, it's astonishing and a really useful reality check because, again, the answer is not either or. We do need those solutions, but it's about where existing approaches really hit those limits and where, new solutions need to come into play. So, climate tech loves optimism. I'm an optimist. But physics obviously still gets a vote, a very strong vote. How do you spot maybe the difference between a hard problem and a dead end?
Yeah, when I lived in Europe, they would always accuse me of wearing American rose-colored glasses. So I'm a consummate optimist as well. And by the way, I think there's nothing to make you more optimistic than being in the innovation and climate tech space, because it's easy to see all these amazing solutions coming down the pipe. And, there's this terminology about, hey, we need a silver bullet for climate change, whatever. And I think it's the height of hubris to think that any one thing is going to be successful. And by the way, in early stage technologies, we have no idea what's going to be successful. So we need silver buckshot. We need lots of shots on goal. However, with finite resources, we should put our support behind the solutions that really can scale to achieve massive impact. And so that starts with techno-economic analysis. This is essentially just determining what the costs of something can be at significant scale. And as the scientists in my life like to remind me, you can apply all kinds of funny accounting to economics and to costs, but there's no escaping the laws of thermodynamics, no escaping the laws of physics. And so, for example, just kind of applying this to some climate technologies. So green hydrogen, electrolyzing water to produce hydrogen is thermodynamically expensive. As the chemical engineers in my life tell me, water is a happy molecule. It likes to stay water. Turquoise hydrogen, which pyrolyzes methane, requires much less energy, about a quarter of the energy. So no matter how much you improve the electrolysis process, it can never be as efficient as turquoise hydrogen. It will always cost more. That's fine. That doesn't mean it's a bad technology, whatever, but it's that these are laws of physics, not of engineering. And so, at Third Derivative, we had to say no to some really cool technologies. For example, in carbon capture, they were great technologies, but we could tell from the fundamental thermodynamics that they were dead ends. They could never get below $1,000 per ton, not due to engineering, but due to physics. And at the end of the day, I'm a capitalist, and I think we need solutions that will pencil at scale, because that's how we'll ultimately have impact at scale.
Yeah, absolutely. I like that framing a lot. It gives people a way to really stay ambitious without ignoring physical reality. And my new favorite phrase is not a silver bullet, but it's silver buckshot. So I'll be stealing that. So on the show a lot. It's an and, not an or. We need all of it. It all comes into play, but I love that silver buckshot. We painted the problem, I think, crystal clear, right? And so I want to get into the material itself, which Galvorn is not interesting because it does one thing well. It's interesting because it combines properties that usually live in separate material categories. So, give us the simple version. What is Galvorn? Why would anyone believe it could challenge materials like copper, aluminum, steel, or Kevlar?
Yeah, so Galvorn is an advanced carbon material that is the highest performing and most sustainable conductor in the solar system, in the universe as far as we know, but we'll stick with the solar system. So here's a small sample of our conductive wire. This is about 150,000 meters, about 100 miles of our conductive wire. So it's about as conductive as copper already today, but 20 times stronger than steel. So 50 times stronger than copper, half the weight of aluminum, lighter even than carbon fiber, and made entirely of captured carbon, incredibly sustainable to produce. It's also incredibly flexible, durable, corrosion resistant, thermally stable. It maintains its properties from near absolute zero to thousands of degrees Celsius, highly thermally conductive. It dissipates heat very efficiently. So it has a lot of really unique combination of properties that make it incredibly effective in some of the most hostile environments that we know of, including outer space. Yeah, and that's because it's a dual-use technology, right? It was funded originally by NASA, the U.S. Air Force, and it was invented by Nobel-winning scientists at Rice University. But now it's commercially available. We're producing it in Houston and scaling it exponentially.
It's absolutely incredible. I appreciate the explanation. It's hard not to get like a little bit excited and giddy about it when you start to learn about it, hear about it, and just the possibilities, which we'll get into. But great simple explanation there. So if you had to pick the one Galvorn property that makes people say, wait, that's possible? Like, what is that? What comes to mind?
You're going to find this a lot. I'm an entrepreneur, so I tend to kind of go against the rules. You're going to ask me to pick one thing, and I'm going to give you a yes and again. I would say it's always a combination, right? There's a multi-property advantage here, in which the whole of multiple properties combined is more interesting, more compelling than some of their parts. So right now, we find it's conductivity plus something else, generally plus one of the mechanical properties. So for example, in aerospace, it's conductivity plus the lightweight. In data centers, it's the conductivity plus the thermal kind of dissipation, because they deal a lot with heat. But if we want to put it all together into one, there's kind of a wonky property called specific ampacity. So ampacity is kind of the more useful or practical form of conductivity. Conductivity is how well something conducts electricity in kind of a perfect state. Ampacity is how much electricity it can conduct before it burns itself up. Because as things get hotter, they tend to conduct more poorly. And then specific means kind of per unit weight. And so the ampacity per unit weight is an area where Galvorn, as far as we know, has, I say, the greatest specific ampacity in the solar system. And so that's one where, when we're talking with aerospace, data centers, power transmission lines, Formula One race cars, their eyes kind of get really big and say, "Oh my gosh, we can do this with just that little bit of material. Let's go."
Absolutely. Absolutely incredible. Again, just to go back to that. And I have another question, but I'll pause for a second because I want to ask this, because I'm sure listeners are wondering, like, what the heck is it? How is it made? Like, what can you share with us that just people can get their heads around of like, okay, now I can kind of envision like what it is.
Yeah, so it's pretty neat. So we start with carbon nanotubes, which are really cool molecules. They're what they sound like at the nanoscale, these little tubes of just carbon. If perhaps you're familiar with graphene, which are sheets, kind of single atom thick sheets of carbon. So if you roll those up into a cylinder, you get carbon nanotubes. And they've got incredible properties, like incredibly high strength, really high conductivity. They're incredibly lightweight and flexible, but they're not all that useful in their raw form because they're highly disordered, kind of aligned in every different direction. So our kind of magic, our secret sauce, is transforming these disordered carbon nanotubes into highly aligned, densely packed, solid materials. So like this wire that you see, that have the same properties, but at a macroscopic scale, at a usable form factor that you can actually do. But we do that by dissolving them down into a solution. We turn it into a liquid crystal, which begins spontaneously aligning these carbon nanotubes. And then we extrude that solution through a coagulant that kind of gets rid of all of the solvent. And all we're left with are these densely packed, highly aligned carbon nanotubes. It is neat. They're not connected by any kind of adhesive or resin. It's just physics. So down at the molecular level, van der Waals forces create these really strong kind of attraction between them, which creates these really kind of strong, lightweight, and electrically conductive materials. It's really rad. But broadly speaking, it's called wet fiber spinning. It's just how other materials like Kevlar and rayon are already produced at massive scale. Our secret sauce is our ability to do it with the carbon nanotubes.
Yeah, I love it. Love it so much. And here's the honest question. Where does Galvorn today beat copper, and where does maybe copper still win today?
Yeah, so copper will still win on, we'd say, volumetric conductivity, because copper is really dense. So if you want to conduct the same amount of electrons under the same conditions as copper, generally you'll need a thicker wire of Galvorn than you have of copper. But you pay this density tax with copper as well, because it's really heavy. And because it's also brittle and it's weak, often we wind up kind of over-engineering, kind of putting band-aids on copper, on shortcomings. So for example, you use thicker copper wires than you really need, or create much larger bend radii because you can't route copper around a tiny little area and bend it or it'll break. Or sometimes you silver plate on top of copper so that you get better kind of thermal performance. Or sometimes you plate copper onto something else that's much stronger so that you get some more strength. So if all you need is a small brittle wire pushing the maximum number of electrons through, copper will be right for the job. But if heat or weight or strength or flexibility or any number of other, or corrosion resistance, a number of other properties are important, that's when introducing materials like Galvorn can be a real winner.
Yeah, absolutely. Great clarification. And I'm sure that's today. We're not talking about, tomorrow, obviously, as things continue to improve. And I think this is going to get other areas where these advantages are going to play in very clearly and easily, as this continues to go. But as we stand today, it's a good, honest answer. I like that as well. A lot of people hear conductivity and they think there's one scoreboard. We've talked a little bit about this, but why is that the wrong way to compare materials?
Yeah. So again, in practical application, conductivity in an abstract sense, in perfect ideal conditions, almost never actually materializes, pardon the pun. So we think about ampacity, for example, let's say so conductivity as it gets hot, because we're increasingly asking for our conductors to operate in very hot environments, whether we're talking about data centers where heat is building up, whether we're talking about power transmission lines in a climate that, again, this isn't controversial, is warming. It's getting hotter out there. Whether you're talking about we're putting more and more conductors in vehicles on the ground, in planes, in drones, spacecraft, these are all areas where they get very hot. So ampacity is one element. There's also kind of the frequency of conduction as well. When we're conducting for data signals, for example, then, and again, seems pretty obvious probably to most people, we're pushing more and more data down the same cable. So we're having to conduct at higher and higher frequencies. These are areas where metallic conductors like copper, not just copper, but like copper, their conductivity actually goes down. They suffer from what's called the skin effect when the frequency gets higher. So when we talk about conductivity, it's actually a more of a multivariable, multi-parameter optimization that you're doing, and there can be trade-offs when you optimize for one versus another.
Yeah, great clarification. And I think helps people see why material comparison is not simple. It's a lot of those different variables that come into play. We talked a little bit about, carbon nanotubes, and I know they've been kind of hyped for decades. Like, what changed that makes this more than a cool lab story now? Like, what changed or developed to make this possible?
I think there really are three things. One is, as I mentioned, the challenge for decades was, hey, these are cool molecules, but what do you do with them? The best thing you could do was really kind of add them to dispersions and add them to something else to kind of imbue it with slightly better properties. So the key unlock here, I would say by our Nobel-winning co-inventor and our co-founder, was the ability to get the same properties from the carbon nanotubes, but in a macroscopic scale, in a usable material that, by the way, drops into manufacturing supply chains that are already known. Like, every manufacturing supply chain knows how to process a wire. We also produce films, fabrics, composites, kind of like carbon fiber as well. So again, there's a machinery, there's supply chains. Everyone knows how to operate with it. Not everyone knows how to operate with a tiny little nanoscale molecule. The other things that have been happening at the same time, quietly in the background, carbon nanotubes as an industry have been scaling up exponentially, reducing cost exponentially, improving kind of quality and properties, maybe not exponentially, at least linearly. So suddenly we find ourselves at a moment in time in which we can take better, cheaper, more abundant carbon nanotubes, process them into solid materials that kind of drop into real applications. And then the third component, I think, is probably more on the demand side, where for all the reasons that I've already described, suddenly we're extremely interested in alternatives to the materials that society has been built on for hundreds of years.
Yeah, absolutely. It's always incredible to see. And again, the reason why you stay really positive in this industry is you stay close to these technologies and seeing how things emerge and how quickly things come about and that things change. What was true 5 years ago is not true today. It's just incredible to see. So you've compared the manufacturing process to wet fiber spinning. You mentioned that earlier, like the process family behind materials such as Kevlar. Why is that such a big deal for scale? So
it's really neat. As a category, as a manufacturing technology, wet fiber spinning is just known to scale techno-economically incredibly well. And it's actually pretty obvious on the face of it if you understand how wet fiber spinning works. Again, it starts with dissolving something down into a solution, then extruding it essentially through a hole into something, like a fiber or a wire. But what's pretty neat is then if you want to produce 100 fibers, you just use a spinneret, which is kind of like a shower head with 100 holes in it. If you want to produce 1,000 fibers, use a spinneret with 1,000 fibers. So you have the same facility, the same plant, you have the same personnel, all you do is change out the spinneret, and then you have, an increased cost of raw materials. But it just allows you to go from kind of ones to tens to hundreds to thousands to millions to, hundreds of millions to billions really rapidly without incurring massive additional cost, without having to, invest in huge facilities. I mean, it's pretty neat. I would invite you or your listeners to come visit someday our production facility in Houston and to be prepared to be underwhelmed, because it's really small. And if we were producing the same amount of carbon fiber, it would be the size of an American football field. But we're producing this much simpler, much more scalable, kind of nano engineered material that fits in, an area not that far from what you're able to see here on the screen behind me.
Yeah, absolutely. I think this makes the scale up story so much more tangible. And for those who aren't watching the video, when you hold up that just kind of spool of it, it's small. You've got it sort of like a foot long, maybe a little more or less or what have you, and how much material is there. It's just absolutely amazing. So yeah, again, something you can hold fits between your shoulders, like small little tube. How much did you say that was in terms of the quantity?
Yeah, so this is 157,000 meters. So it's about 100 miles of conductive wire. And just as an exercise, I would challenge anyone to try to find 100 miles of copper wire or steel wire or even aluminum wire, which is relatively light, and try to pick it up. I'm sure you have some really strong listeners, but that's not going to happen versus something that I can, toss over my head.
It's remarkable. You're just handling this thing. It's small. You can see it, which is absolutely amazing. So as we've talked through, so this real test for new materials, not whether it just sounds impressive, but we're talking about real scale, and it's really whether customers can qualify it, trust it, design around it, and buy it at scale. What was the first customer use case that made you think, yeah, this has happened? Like, this is not science fiction anymore. This is it.
I would say there were a couple of use cases where it really clicked. Like, okay, this is the only material in the world that can do this. And now this entire application area is enabled. One was, so with the US Air Force, we produce a cathode it's a fabric of our material, a cathode that's used without getting too wonky, a directed energy defense for incoming drone swarms. And so they needed something that was conductive, like really conductive. They just sent a lot of energy, but also had to be really flexible because we had to make it into a fabric, and also to be really lightweight because you had to transport it around a battlefield. I mean, maybe the drones are coming from over there, now they're coming from over there. And there was just no other material that checked kind of all of those boxes. Or similarly, we have a medical device customer that we work with called Neurobionics, and they're obviating the need for open brain surgery for deep brain stimulation and other neuromodulation. So instead of opening up the brain to install an electrode, they're catheterizing a tiny wire of Galvorn up through the neck, targeting the exact same part of the brain, sending the exact same electrical signal, but they need something that's obviously very flexible, really small, has to be really strong. You can't have it break off in there, and it has to be biocompatible. And ours is made of pure carbon. So once again, it was kind of like, okay, there's nothing else in the world that can do this. But probably the biggest one, and we're not quite there yet, but we have we're working on a lot of DOE funded work to bring this to market, is actually power transmission line grid applications. So we already don't use copper for power transmission lines because it's so heavy. So instead we use aluminum, which is much lighter, but then we wind up putting kind of Band-aids upon Band-aids upon Band-aids. The aluminum is light, but it's pretty weak, and it expands as it heats up. You've seen these power lines sag, so it has to be reinforced by steel that goes down the middle of it. Okay, now you've got steel down the middle. Now you've got to have a sheathing between the steel and the aluminum so there's no galvanic corrosion. Okay, all right, and then we're trying to move from steel to things like carbon fiber composites, which is great, but they're really brittle. So now you've got to install a bunch of sensors to make sure you know if there are any line breaks, whatever. So it's Band-aid upon a Band-aid upon Band-aid, and we're just looking at this. Well, wait a minute. We got one material. You can just string it up from one to another. And by the way, it's so much stronger and so much lighter that you can put the towers much farther apart. Like it's inevitable. It's a question of when, whether it's Galvorn or something else like it, we move away from this 100-year-old technology that we're using for power transmission lines to something much more modern.
Yeah, it's absolutely just mind-blowing. When you look at the different use cases, how it's being used, and some of those breakthroughs that are happening, it is just I don't know, it sounds like a science fiction material, but it's real, it's here, it's there, and scalable. So it's absolutely amazing. In wire and cable, what has to happen before a serious manufacturer stops saying, okay, interesting sample, and starts saying, we can build around this?
So a few things I would say. The first is there has to be some really rigorous testing and qualification and specification. It's one thing for us to make some bold claims on our website. It's another thing for them to say, this is dependable enough that we really know what the properties are. So third-party testing is really critical. Then there has to be productization as well. I mean, we're not producing a product. We produce a semi-finished good that gets designed into products, by our manufacturing partners. So we just signed a JDA with one of the world's largest and most significant wire and cable connectorization companies. So they do they'll take a material like this and then they'll insulate it, they'll terminate it with the appropriate connectors, and then we'll provide a lot of specifications, like 20-page documents about exactly what the properties are, how to connect it, how to work with it, et cetera, which is what customers expect from other materials. But then if you've got a customer that's really looking to move from the development phase into mass manufacturing, then the requirements really become about quality management and quality consistency. And so it was really neat working with neurobionics because, implanting something in the human brain requires extreme quality control and quality consistency. And so as part of we just signed a multi-year kind of purchase agreement with them. As part of that, we achieved our ISO 9001 certification for quality management. So that provides kind of a stamp of approval that customers understand, okay, we're going to get the same thing every time. It's going to be within tolerance. And if not, there's some recourses for it. And then you've got to be able to demonstrate, a consistent price or consistent supply over multiple years. Because if someone's building a product and taking it out to market, they need to know that you're going to be there for them the next year and the next year and the next year. And so, as I mentioned, we just signed such an agreement with Neurobionics. We had a few more that are coming down the pipe as well.
Yeah, absolutely useful insights there. So you've been on the other side as well too. What do people outside hard tech maybe completely underestimate about getting a new material approved for aerospace, defense, grid, automotive, or medical use, as you just started to touch on there?
Yeah, I think there's often an assumption that it's just going to be about kind of technical hurdles or maybe even price hurdles, but actually there's a lot of onus on the supplier that is financial. They have to make sure that you're still going to be there the next year and the next year and the next year. And if you're selling to the federal government, Department of Defense, or Department of Energy, as we are, they need to make sure you're going to be there, 10 years plus from now. So they want to dig in a lot to your balance sheet and your, investors and who's behind you, et cetera. So we're really glad to have some really strong backers. Like Shell, for example, was global multinational, was one of our early investors. We have a lot of support from the Department of Defense, Department of Energy. And so those add a lot of confidence to customers who want to make sure that even as a small and scrappy startup, you're still going to be there in a few years and they can really invest in taking a material to market.
Yeah, good points. And then discussing some of those hurdles that people probably don't think about, and especially like the financial, livelihood and stability of the organization as well too. So you've talked about dramatic scale up and cost reduction. What's the next milestone that would make, any skeptics out there just take Galvorn even more seriously over the next 2 years?
Yeah, and maybe just a little historical context so we can understand, humans, we tend to struggle with exponentiality, but this is an incredibly exponential technology. So this spool that I'm holding right now, 150,000 meters, 3 years ago, so before we raised our first round of funding, this would have cost hundreds of thousands of dollars and taken us 6 months to produce. So kind of on par with mythical materials like unobtainium. We've scaled up 3,000x our production capacity and reduced costs more than 100x kind of over those 3 years. So we've gone past exotic materials like gold and silver, and now we're at cost parity with, say, specialty materials like silver-plated copper. And then we're going to do that again over the next couple of years. And today we produce this for a few $1,000s in less than an hour. And a few years from now, we'll produce this much every second for less than $1. So actually less expensive than even commodity copper, steel, and aluminum, which again, just to bring the conversation full circle, just comes down to fundamental thermodynamics and technoeconomics. This is just a fundamentally more efficient material to produce than metals. But the scale is continuing. So we're recording this in July. It's not quite over yet. And it's already our biggest sales month on record. It actually would be our biggest quarter on record and bigger than any of our prior years, except for 2025. So, we're expanding on the demand side, on the supply side. And, in 24 months, what we really think of though as kind of markers for how well we're coming along is where Galvorn is commercially deployed. We have high certainty at this point that it'll be deployed on the moon at that point and it'll be headed toward Mars. But in our defense, because we'd like to see it deployed in active theaters, like in Ukraine. And certainly we use AI a lot in our company. We'd like to know that Galvorn is inside the data centers that are responding to all of our queries.
Absolutely. Again, remarkable just progress and scale, and then seeing that timeline as well too, and what's coming and what is going to be with the material is absolutely incredible. So we'll bring us back a little bit to climate. Climate wants speed, but materials demand proof. How do you build urgently without overpromising?
I think you just build urgently. And I think you do overpromise, and then you find ways to fulfill and deliver on those promises, and not out of hubris, but that's just what the problem demands of us. Bill McKibben has this great quote, and I think about it every day, that when it comes to climate, winning slowly is losing. And so if we're not out there trying to push the envelope every day and then push it a little bit farther, I don't know what we're doing. And so we probably have a number of things that we could be doing better, but at least as of this moment, we've achieved a production capacity that's on par with, other companies. It's taken them orders of magnitude, more capital, more headcount, and more time to get there. I'm hopeful that, there are others that will come along kind of behind us and do the same and do it even faster and better, because we don't have the time for it. So I don't think it's a trade-off or a tension between urgency and overpromising. I think we've just got to make the promises, and then we go out and find a way to make them true.
It's really good. I did not know you were going to go that direction with that, but that was incredibly powerful and well said. And that'll definitely stick with me as you just shared that and agreed. So as we talk through, you've seen climate tech from more angles than most people, from founder, investor, ecosystem builder, now deep tech CEO. And I think that gives you a unique view into what it takes to actually scale a moonshot, as we've been talking about. So being a founder, investor, accelerator builder, now a deep tech CEO, what do investors still get wrong about materials companies?
Yeah, I think there's kind of a reason why materials are generally brought to market by existing big materials companies rather than by, spin-outs and startup. I think there's a lot that traditional investors don't appreciate about the path to market for materials. And so investors often want to see you kind of de-risk the market by making sales today, at today's scale, at today's prices, even though the investable opportunity isn't for the tiny markets that can buy at today's prices. They're for the much larger scale and much lower price. And so, but it's super understandable, right? Like we've got Nobel winning science here. It can be hard to wrap your head around. What's one thing that investors can all wrap their hands around? Revenue. And so, 9 times out of 10 from investors, they'll be asking, how much revenue have you made? How much revenue have you made today? And it's the wrong question for a venture that's early stage in the material space. It's really should be more around how many partnerships have you created with wire and cable manufacturers? How many customers do you have already starting to design in and test and qualify your material? But so we're really proud to have a really strong contingent of investors. I mentioned Shell already, Nonsibi Ventures, who led our last round, Tailwind Futures, Better Way. I mean, these are really visionary investors who get it and get what it's going to take to have kind of massive climate impact at scale. It's going to take really big ambition and kind of getting toward those much lower cost points and the much larger scales. Those are the markets that we really care about.
Absolutely. I think really helpful for investors listening, because materials companies, again, don't always fit those similar expectations with other types of companies, but the risk is different. But again, that potential impact can be foundational if the material becomes part of the industrial stack and scales and all that as well. So you've said climate commercialization is a team sport, and you touched on that a little bit earlier, but who has to show up for materials moonshot to just actually scale and make it?
Yeah, there's an expression in the startup world about the valley of death. And our perspective at Third Derivative was that for deep tech ventures trying to solve climate, there are multiple valleys of death. There are actually 4 distinct valleys of death. You got to get a company, spun out from a university or a national lab. You got to get it kind of early funding and a team built around it, kind of a prototype developed. Then you got to get out and start developing some commercial traction. And then you got to get out and scale it. And what it takes to be successful in making it across one of those valleys of death is not the same thing that it takes to be successful in the next one, which is not the same thing that it takes to be successful in the others. And yeah, especially in deep tech and in climate tech, it's really hard for like a solopreneur just to go out and turtle themselves in and go have a successful company. There are all these dependencies on others, certainly on financiers, because generally paths to market are long and capital intensity is high. Often with corporates as well. Corporates are generally going to be the customers, the development partners, the deployment partners, in many cases, even the acquirers of these types of companies. And then it's important to have the policymakers at the table as well. For many types of climate tech, policy is a really significant lever. And unfortunately, policymakers are often making policy based on the technology from 30 years ago, and we need them to actually start skating to where the puck is going, or at least catch up to where the technology is today. So our philosophy at third derivative was that, that it's a team sport, not an individual sport. We need all of these players at the table, and we need to be orchestrating them, getting them all to kind of move in lockstep together rather than fumbling the ball between them. But if we could do that we could have better and faster success stories in commercializing, deploying, and rapidly scaling climate tech innovation. And again, there's a lot more that still needs to be done, but I think we demonstrated it with billions of dollars into hundreds of climate tech ventures.
Yeah, great perspective. And I think that ecosystem view is really critical. It's a great reminder that climate innovation is not just invention, it's coordination, that the orchestration of all those different parties as well too, and what goes into that. So be honest here. So what is building DexMat demanded from you personally that your earlier software and climate tech chapters did not?
Yeah. So again, a former American football player here, and even more than a football player, I was a fullback. So I was a blocking back. Send me in the hole first. I'm going to clear it out so that someone else can go get the glory and score the touchdown. So I have a leadership style that tends to be kind of leading from the front. And in my software days, that was easy to implement, right? Because oh gosh, we're running behind. We got a big deadline. No problem. I'm going to roll up my sleeves and be there all night or over the weekend and get it done. But I can't do that with DexMat. I can't lead from the front with Nobel winning scientists and PhD chemical engineers and nanochemists all around me. So I've really had to learn to let go of some things and really trust the amazing, brilliant, committed, mission aligned team that's around me in that case, which has been an interesting exercise for me kind of psychologically. But also I'd say as someone with a software background, it's sort of neat to be building deep tech at this moment in time, because I'm building a lot of software, again, probably for the first time in more than a decade. I'm using a lot of AI. We're building software for our team. We're building software for our customers. We're building software, for engaging with our investors as well. So it's kind of like I've had to kind of set something aside, but then I've also kind of recaptured something that I thought I had set aside previously. And then, on a personal front, I travel a lot for DexMat. I mean, we're working on a global issue. We've got customers, investors, suppliers, kind of all around the world. And I've got 2 small kids whom I adore. I've got an amazing partner whom I'm not trying to leave as a single parent. And at the same time, I look at the travel and the commitment to DexMat and the mission that we're on as really, an expression of my values that I want those kids to see. We believe in living a life of service and adventure and mission orientation, not of comfort and convenience. And sometimes there are trade-offs that are necessary there, but I hope that they see that and that someday they'll wake up and find their moonshots that also they want to be really committed to.
Yeah, I really appreciate that honesty and you sharing that. And I think that personal side really matters. Moonshots can sound glamorous, but the work is demanding, does require a different set of skills, some sacrifices, but your why is so strong and the work that you're doing so important. So again, wanted to get that out there. So to close, I want to just zoom out a bit. I think if you're right about this, materials are not a side story in the energy transition. They are just fundamental as a part of it and maybe one of the defining stories of the next industrial era. So if the world finally accepts, the energy transition is also a materials transition, those two are married and intertwined, what changes first?
I guess my hope would be, and here I might be a bit optimistic, but my hope would be that the recognition that was the case and that we kind of took our eye off the ball there for quite some time would help at a society level for us to step back and start making decisions, starting with first principles and not starting from the just inertia of what we already have going. And in many cases, that would lead us, I think, to evaluating materials and energy and kind of fundamentals like that. But if we could get to a point in which we were starting with first principles and letting that shape investments of capital, shape investments in innovation, shape trade, shape industrial policy, I think that could be profoundly transformational for us at a societal level and at a time where we desperately need it, where kind of every day that goes by that we're not taking the action that we need on climate is a day that's going to make the next day kind of even more challenging, a bigger hill to climb.
Absolutely. It's a hopeful and powerful shift, I think, and makes the opportunity feel a lot bigger than one company. It's about changing how the whole system thinks and what's going to be needed there. Final question here is if Galvorn and materials like it scale the way you believe they can and will, what does the world look like 10 or 20 years from now that would surprise people today?
Yeah. So, 10 or 20 years out, Galvorn and let's say materials like Galvorn will be higher performing, more sustainable, and less expensive and more, abundantly kind of sourced in feedstock than every major material that's on the market today. So at that point, a conversation with a me or my counterpart at some other, materials company is not going to be limited to conductive wire and cable in, drones and data centers. It will really have expanded out into structural applications. So you'd imagine a world in which bridges, buildings, vehicles are made out of materials like Galvorn. I think there'll be some inequity that happens because economies that are still building themselves on kind of low performing, dirty and expensive materials simply, won't be competitive. Ideally, these types of materials are accessible to everyone. And there's all these, inertia and supply chains, et cetera. I would be surprised if the switch happened overnight. But I think what'll be really interesting, it's easy when you have a new material to start just saying, okay, well, what can we do that we're already doing better with this material? But what gets really interesting is, wait, what are we unable to do today that now we can start doing with the new material? And, in a classic example over history, so for thousands of years, humans made bridges with rocks, with stones. And so we used arches to take advantage of the compressive strength of the stones. When we invented steel, we didn't start making steel stones and keep using compressive strength. We took advantage of the tensile strength of steel, and we invented an entirely new design paradigm of the suspension bridge. And so it's sort of the same. When we talk about making buildings with Galvorn, and we already have architects who are designing them, and they're wild and beautiful. You don't just take a steel I-beam and make it out of a composite of Galvorn. You actually design the building in an entirely different way that takes advantage of the strength, of the lightweight, of the flexural tolerance, et cetera. And so you can imagine these kinds of kind of trickle down effects. And we say, okay, well, we're going to start making buildings out of Galvorn. That's great. Now the buildings can go, kilometers up into the air because they're so strong and they're so light. Okay, wow. But if we have people that are literally kilometers up in the air, I'm not sure we want them sitting in an elevator for, half an hour just trying to get up and down. Great. Galvorn or materials like Galvorn also have enabled flying cars because we've solved the kind of power to weight ratio. So suddenly we can go, we can fly around. Oh, but wait, maybe we don't even need flying cars because, we can do a full on space elevator kind of all the way up to space and we just have people living alongside. Anyway, it starts really to get into the realm of science fiction, but I think there's a takeaway, and you mentioned it earlier, like this stuff sounds like science fiction, but it's here. I mean, what's the expression? The future is already here. It's just not evenly distributed. Science fiction is science reality. And there are these inflection points that are very nonlinear, just like the exponentiality of the production here. As this begins to take hold, as one thing is designed with it, suddenly other things around it will become designed with it. And we'll see some radical wholesale innovation of just the way that we build society. And I'm here for it. I'm excited for it.
Absolutely. I'm here for it as well. And that is such an inspiring place to land. It brings the conversation back to possibility and science fiction being, it's real, it's here, it's arrived. But I love that vision. I love the vision for the future and what can be. And I think that is such an exciting part that I can't wait to just continue to watch the story and continue to watch this unfold. But Bryan, this was incredible. Thank you for helping us see the energy transition through a completely different lens. This was a conversation about copper, carbon, data centers, hard tech, and climate, but more than anything, it's about what it really takes to build the future and what's possible. To everyone listening, if this episode changed how you think about materials, electrification, or climate innovation, share it with someone who needs to hear it. Thanks for listening to Green Giants Titans of Renewable Energy. Subscribe, rate the show, and we'll see you next time.
This episode of Green Giants, Titans of Renewable Energy, was brought to you by Lee Group Search. If you enjoyed today's discussion and are looking to recruit top talent for your company, or find your next career opportunity in the renewable energy sector, visit leegroupsearch.com. Let's continue driving the future of clean energy together. Until next time, keep pushing toward a greener future.